so small, in fact, that we call them fundamental, which means we can no longer break them down. Each one of these 15 fundamental particles are organized into 3 groups: leptons, quarks, and gauge bosons. The first group, leptons, are characterized by their 1/2 integer spin. This is comprised of electrons, muons, and taus. Muons and taus are just higher energy versions of electrons. Each one of these particles has a respective neutrino, which is a massless version of the particle that only interacts with these particles. So they do not interact electromagnetically. They were also originally believed, until earlier this year, to have the potential of not carrying any mass. However, that has been shown wrong, and a Nobel Prize has been awarded for that. The second group, quarks, are also characterized by their 1/2 integer spin. This is comprised of up quarks, down, charm, strange, top, and bottom. The up and down are what we tend to observe in our normal situation every day. 2 up quarks and 1 down quark makes a proton. 1 up quark and 2 down quarks makes a neutron. And each one of these particles inside of the neutron and proton are held together by what are called gluons, which we will get to later. The last group, gauge bosons, is characterized by its 1 integer spin. This is comprised of 5 particles and theoretically a 6th. The first are gluons, which are responsible for the interactions inside of a nucleus between quarks. The second are photons, which are responsible for being the force carriers of the electromagnetic force. So interactions between molecules will hold different molecules together. The third, W and Z bosons, are responsible for interactions between fermions. The fourth is the Higgs boson, which is an excitation of the Higgs field, and is popularly described as assigning fundamental particles mass. The 6th particle has yet to be discovered and is currently being experimented, trying to find it, is the graviton. And upon its discovery, will complete the Standard Model's ability to describe the 4 fundamental forces that we know of. That is strong, weak, electromagnetic, and gravitational.
In his paper, Unraveling Hadron Structure with Generalized Parton Distributions, Bielski opens up discussion about using generalized Parton distributions to develop a 3-dimensional model of the nucleon and allow measurement of quark orbital angular momentum and inter- and multi-parton correlations. This method is nothing new and has been used since the 1970s to better describe the behavior of hadrons, which are particles composed of quark clusters, neutrons being under this group. On November 9th of 2015, Cecilia Lunardini presented in her paper a new calculation of emissivities of stellar evolution with regards to neutrinos and beta decay. She found that beta processes contribute more to the neutrino flux than was previously thought. The effect is a better approximation of the emissivities occurring in supernovae. These emissivities being beta radiation, which are when protons decay into neutrons, and the net energy of an atom changes in the form of radiation.
Thank you for watching.
Have a wonderful break.
Thank you, Dr. Z.
Z.